In this video, we'll talk about some general notes for using the graph of y equals f of x to sketch the graph of y squared equals f of x. A lot of these techniques we saw in the previous example, so let's just talk about them in general note form. So the first one, identify all of the points where y equals f of x is below the x-axis. These values of x will not exist on the graph of y squared equals f of x, because f of x needs to be greater than or equal to 0 if y squared is equal to f of x for some value of y. So basically, if f of x is less than 0, then there is no y coordinate such that y squared is equal to that f of x value. So therefore we cannot have an xy pair. That satisfies the equation. Okay, the next point. Identify all the points on the graph where y equals f of x and y squared equals f of x intersect one another. These will be the points where f of x equals 0 or f of x equals 1. Because if f of x equals 0, then setting y squared equals 0 also gives y equals 0. And if f of x equals 1, then setting y squared equals 1 gives us that y is equal to plus or minus 1. So it's still going to go through the point, whatever the x coordinate was, to make f of x equal 1, and then it's going to have the y coordinates positive 1 or negative 1. It's easiest just to deal with all the positive y values first on the graph of y squared equals f of x, and then just reflect it about the x-axis at the end. Alright, next up. Identify the stationary points of y squared equals f of x. The stationary points of both graphs will have the same x-coordinates, but the y-coordinates will be different. If a stationary point of y equals f of x has a y-coordinate of a, then the corresponding stationary points of y squared equals f of x would have y-coordinates plus or minus the square root of a. Let's go ahead and prove the first part here. The stationary points of both graphs will have the same x-coordinates. So to that end, let's suppose that x equals b be a stationary value of y equals f of x. So that would tell us that f prime of b is equal to 0. Now if we consider the graph of y squared is equal to f of x, and we want to differentiate that, then we get, well, using implicit differentiation, we get 2 times y times dy over dx is equal to f prime of x. And so that tells us that dy over dx is equal to f prime of x divided by 2 times y. Now be careful, this y is not the same as this y over here. In fact, if we were trying to write it in terms of f of x, it would be f prime of x divided by 2 times plus or minus the square root of f of x. But for this argument, there's not much need to go into that detail. So the point is, as long as our y-coordinate in this graph does not equal 0, and if it did, we would also have f of x equals 0 at that point. But let's suppose y does not equal 0, then clearly dy over dx at the point x equals b is equal to f prime of b divided by 2 times y, which is equal to 0, since f prime of b equals 0. So if x equals b is a stationary value of y equals f of x, then we also have a stationary value at x equals b in the curve of y squared equals f of x. So long as f of b does not equal 0. Guess I should have included that as a condition. You know what, let's say f of b is greater than 0. Because if f of b is less than 0, then we're not going to even be considering it on our graph of y squared equals f of x. And just working in the opposite direction here, clearly if we have a non-zero stationary point on the graph of y squared equals f of x, then we must have that f prime of x equals 0 at that point. So it's also a non-zero stationary point on the graph of y equals f of x. I'll leave it to you to investigate the case where f of b is equal to f prime of b is equal to 0. What happens there? You might want to start out by checking out the graph of y, well, the graphs of y equals x squared and y squared equals x squared, and perhaps y equals x to the 4 and y squared equals x to the 4. And just finishing off this point, we said that the y coordinates will be different. If a stationary point of y equals f of x has a y coordinate of a, then the corresponding stationary points of y squared equals f of x would have y coordinates plus or minus a. I think that one is fairly simple. So let x equals b be the stationary value of y equals f of x. Then that means that f of b is equal to a, and we proved that it's also a stationary point of the curve y squared equals f of x. And so since y squared is equal to f of b, which is equal to a, at that point we must have that y equals plus or minus the square root of a. And again, a is greater than 0. Okay, moving on to the next point. Look at the gradient of the points where f of x does equal 0. Now, unless the gradient of y equals f of x is 0, then the tangent at these points is parallel to the y-axis. And I've asked why here, so you should pause the video and see if you know why. Well, we already kind of dealt with it a little bit here. If we have the curve y squared equals f of x, then we determined that dy over dx is equal to f prime of x divided by 2 times y. So y squared is equal to f of x implies dy over dx is equal to f prime of x divided by 2 times, and we can write it in full this time, the square root of f of x, positive or negative. And now let's go ahead and prove this point here. Look at the gradient of the points where f of x equals 0. Unless the gradient of y equals f of x is 0, then the tangent at these points is parallel to the y-axis. Well, let's suppose f of c is equal to 0, and f prime of c does not equal 0. And let's let x tends towards c. Then what does dy over dx tend towards? Well, on top here, we have that f prime of x just tends towards f prime of c. So some fixed real number. But meanwhile, on the bottom, whether we take the positive or negative square root of f of x, this thing is tending towards 0. So that means that dy over dx is tending towards something undefined, which means that it has to be vertical, because that's the only way it can have an undefined gradient. And so that takes care of this point here. If f of x equals 0, then unless the gradient of the graph of y equals f of x is 0, then the tangent at these points, and I guess to make it absolutely clear, I should say in y squared equals f of x graph. So the tangent at these points in the y squared equals f of x graph is parallel to the y-axis because it has an undefined undefined value of dy over dx at these points. And we saw it in the last example when we were sketching that kind of oval shaped thing in the middle. We really should make it so that it comes down and just reaches a sort of vertical tangent there at that point. So it should be a proper kind of oval. So that was from the previous example in the previous video. And lastly, I think this part is fairly self-explanatory. To sketch the parts of the graph that is above the x-axis, if 0 is less than f of x is less than 1, then y squared equals f of x is above y equals f of x. And if f of x is greater than 1, then y squared equals f of x is below y equals f of x. Now, there's one point I've left off that I probably should have included. I've kind of alluded to it, but it probably belongs on this list. Pause the video and see if you know what it is. I think it follows on nicely from this last point. Sketch the parts of the graph that are above the x-axis. So then the final point would be sketch the parts of the graph below the x-axis. And we do this just by reflecting the parts above about the x-axis. And then we're done.